This is video 6 for chapter 20, and in this video we are going to learn how to relate the term free energy, which you learned about in chapter 19. So you'll remember free energy is delta G, and we're going to learn how that ties in to our redox reactions. So you might remember from chapter 19 that delta G is able to tell us whether or not a reaction is spontaneous. So if a reaction is spontaneous, it has a negative delta G value as written. The forward reaction would be spontaneous as written. If the delta G value is positive, then that reaction is non-spontaneous. So keep that in mind as we go through this. In this chapter, what we've learned all about is cell potential, or E. And sometimes it's E standard, and sometimes it's just E if it's at non-standard conditions, but we've pretty much focused our studies with Appendix E. Okay, so all of these values you might be remembering are coming from Appendix E in the back of your textbook. And the formula we've used so far is that the E of any cell can be calculated by taking the reduction potential for the reduction process, which you might remember occurs at the cathode, and subtract from that the cell potential or reduction potential for the oxidation process, which occurs at the anode. So always remember cathode minus anode. And this is what you watched in the last two videos, was how to figure out cell potential. Now, we already know, hopefully, that if you have a positive cell value for E, that you get a spontaneous process, and that means like what we utilize in a voltaic cell. So all cells should have a positive voltage. If you get a negative voltage, or E cell is negative, then it's a non-spontaneous process. Now, we're going to use an example to try to help understand how this works. So let's look at this nickel and silver reaction right now. If we look at this one, maybe without me doing this for you, just pause the video right now and just try to identify for yourself which of these two species, nickel or silver, is being oxidized and which one is being reduced. So if you pause the video and figure that on your own, and let's see if you're right. When you're ready, you press unpause. So right now with nickel, if we look at it, nickel is in the solid state to begin with. So we would assign it, because it's a metal in a solid state, a oxidation state of 0. Over here on the right hand side, it has a +2. So we would say that that nickel is being oxidized, and hopefully you remember that oxidation always occurs at the anode. Now let's look at the silver. Silver starts as a +1 over here and finishes over here as a 0 because it's in its standard state. So the silver was reduced, and we know that reduction always happens at the cathode. So if we look at this process, if we want to figure out its standard cell potential, this is kind of a review from what you saw in the last video, you would know that to calculate E cell standard, we're going to use the reduction potential for the process that occurs at the cathode minus the reduction process, or the reduction potential for the process that occurs at the anode. So you're going to use your Appendix E values to find these numbers. Now, you should look them up in your book just to make sure you're really looking them up correctly. But this reduction potential at the cathode, if I look for silver, silver has a voltage listed as 0.799 volts, and that's a positive number, and we want to leave these numbers as is as they show us in the table. For the anode, the nickel process has a voltage of negative 0.28 volts. So when we do this math, we should get a voltage of, it's confusing, 1.079, and I'm apologizing for the smartboard. You guys know that this isn't behaving the way it should. Volts. Now we want to be careful with significant digits, so since we have 3 decimal points in one of our voltages but only 2 in the other, technically speaking we can really only report our answer to 2 decimal places. So I'll leave this as 1.08 volts. Now, because that is a positive voltage, we now know that this reaction is spontaneous. And so if you think about what you learned in the previous chapter, chapter 19, if you could predict a sign for this delta G value, you should predict that it's negative, because spontaneous reactions have delta G values that are negative and E values that are positive. So we're going to try a practice problem where I have given you 3 individual reactions, and I want you to tell me, based on the way that they are written, are they spontaneous or not under standard conditions? I'm just going to do part A with you, and I'd like you to try B and C on your own. But you're going to find Appendix E will be very helpful, because some of these half reactions are fairly complicated, and so it might be helpful to look at Appendix E to make your life a little easier. So if we look at A, it's easy maybe to identify the copper components as part of a half reaction. So I'm going to start with that one. On the left-hand side, I have 5 Cu plus 2 aqueous. And on the right-hand side, that's just 5 Cu solid. And I'm going to keep the 5s there because that's how it's balanced in the equation. Now, what is missing in terms of this half reaction? Well, the atoms are all accounted for. You have 5 coppers on each side. But what's not accounted for is the charge. This side has an overall, the left side has an overall positive charge of 10. So I have to add 10 electrons to that side. Now, when it's written like this, that's not very clearly written, but when it is written like this, with 10 electrons, as a reactant, that is being given to me as a reduction potential in this problem, and I would look it up in Appendix E, look for an equation that matches this. Now you might want to reduce this, so instead of 5, 10, and 5, you're looking for 1, 2, and 1. But when you find it in Appendix E, you should see that it has a value of positive 0.337 volts. Now the other half reaction would involve everything else, and so you can see the things that are remaining in the half reaction. And it is a little bit confusing because if you look for this reaction in your textbook in Appendix E, it's actually written backwards. So I'm going to write it that way. This is how you see it in Appendix E. And I want you to think about, why is that? Why is it backwards in Appendix E? And the answer is that everything that's in Appendix E is written as a reduction reaction. So that's why both of them are showing electrons being gained. Okay, so to finish this off, oops, that's a solid. If you look at this one, this is probably exactly how you're going to find it in the book, because this really can't be reduced any further than it is right now. So look for this in Appendix E, and you will see that it has a reduction potential of a positive 1.195 volts. Now we want to see if the cell, as written, is spontaneous, or if it's not. So look at your actual reaction. In your half reactions, both are being written as reduction. Both can't be reduced. So let's look at what's really being reduced in this problem. The copper is really the one being reduced. So that's the one that's happening at the cathode. Reduction always happens at the cathode. So remember, for each cell, I'm always going to look up the reduction potentials for the cathode minus the reduction potential for the anode. And the reason I was able to figure out which one is the cathode and the anode in this problem is because I'm just using the reaction that was given to me. It's clear from my reaction in part A that copper's going from a +2 down to a 0. So I have to make that my cathode. So I'm going to use my value for copper, which was 0.337 volts. And I'm going to subtract from that 1.195 volts. And you're going to see that you get an answer of negative 0.858 volts. And because this is a negative E value, we would say that this reaction is non-spontaneous. So the way that it's written, this reaction is non-spontaneous. I would like you guys to pause the video or come back to it and try parts B and C on your own. We're not quite finished, however, because we do need to make this related to delta G. So here's your equation that you need to write down. Delta G is equal to negative N times F times E. And all of those variables are explained to you there. So delta G, you already know, is Gibbs free energy. Number N is referring to the number of moles of electrons transferred. F is a new number for you. It's Faraday's constant, and you do not need to memorize it. And E is just the EMF of the cell. Now, we define this here as a Faraday is going to equal 96,500 coulombs per mole of electrons, which this is probably not that clearly written here. So this is the way you'll use it in equations. 96,500 joules per volt times mole of electrons. That's the constant you want to know. So remember that if N and F are positive, then delta G would be negative and E would be positive. This reaction has to be spontaneous. So we're going to try one practice problem. For the same reaction I just worked you through on the previous problem, the same part A that we looked at before, what was the value of N? So let's look back at that problem you did just a few minutes ago. Here, in our green reaction, we see 10 electrons, and in our red reaction, we see 10 electrons. That's what got this to balance. So the question that was being asked, what is the value of N? The answer is A, 10 moles of electrons. And in B, they just want me to find what delta G is. So delta G is equal to the negative N times Faraday's constant times the E of the cell. So we already know that negative 10, or 10 is our number of moles of electrons. Faraday's constant is 96,500 joules per volt mole of electrons. And then the cell potential, normally we would figure out, but we just did that in the previous problem. It's the same equation. So we can say our E cell was negative 0.858. So I'm going to plug that number in. And that's in volts. So if you look at your labels, moles of electrons will cancel. Volts will cancel. And so your answer for delta G, like it was in the previous chapter, should be in either joules or kilojoules. So if you do this math, you get 828,000 joules. But if you'd rather report that in kilojoules, which is usually how it's done, you'd get 828 kilojoules. Now, that's delta G. Since delta G is positive, this reaction was non-spontaneous. And we also knew that because the E value was negative. So hopefully now you know how to use this equation to relate delta G to E.